All right, so the first way that we can determine reaction rate is by actually measuring them. So doing this in the course of a reaction. Remember that I said earlier that sometimes concentration affects the rate and sometimes it doesn't. And concentration can also affect the rate to a different extent. And we can't always tell just by looking at a reaction. So it does have to be measured. One way that we can measure a reactant, like let's say it was a gas that was being formed, we could withdraw samples and measure the concentration over time, and that's just one way to do it. An easy way, and one that we'll probably be using in lab, is to look for color changes. So if you have a reaction that either increases color or decreases color, you can either monitor it by sight, as you can see here, see how long it takes for the color to disappear. Sometimes you can also monitor it by instrument, because they can measure colors too, and so you can measure it over time. Yep, so the gas phase, partial pressure if it's a gas. What we can do is we can measure pressure readings of all the gases over the course of the reaction of the 3 different ones and see what their changes are. Like I said, colorimetry is where you can measure the color. This is just an example of it. The IO negative absorbs light near 400 nanometers, and so you can measure that with an instrument. I'm trying to think, I can't think off the top of my head. I guess it's in the red zone. So you may be able to do it with your eye, or like I said, with an instrument. We're not going to be doing any of this except mostly just by eye that I know of, and we're not going to do any kind of gas measurements. Those are kind of difficult. And so like I said a little while earlier, a lot of times what we have to do is run a reaction to find out what its rate is, how concentrations affect the rate. And so the rate of a reaction depends on the concentration of the reactants as well as catalysts, and we can see it experimentally. We can't predict it. And so what we're going to do is look at how we can find the dependence on concentration by looking at experimental data. So let's look at this reaction of nitrogen dioxide with fluorine. So here's a reaction. Turns out that the rate of this reaction was done experimentally, and it turns out that it's proportional to the concentration of nitrogen dioxide. Or more specifically, if you double the concentration of NO2, what happens is the rate also doubles. So if you increase the concentration, you increase it by a factor of 2, everything will go twice as fast. It turns out you can also vary, and we'll look at this more closely in a minute, you can also vary the concentration of F2. And it turns out that if you double the concentration of F2, the rate also doubles again. So what we want to get from that information is a mathematical expression that will relate the rate of the reaction to the concentration of the reactant. And this is what is called a rate law. So the rate law is an equation that relates the rate of the reaction to the concentrations of the reactants, and the reactants are raised to some power. In this case, they happen to both be 1, but we're going to be finding that out. And so they're related mathematically. This is just a constant. K is the constant. Notice in the case of the last reaction, these are the 2 reactants. Sometimes catalysts are involved, sometimes not all the reactants are involved, but a rate law, just so you know what a rate law is, it's always in the terms of rate equals some constant times the concentration of the reactants and sometimes catalysts to some power. And the first thing we're going to do is look at data and try to figure out what the rate law is. And then we'll also use rate laws later on. And so again, K is just a constant, and it'll be particular for that particular reaction. All right, so let's look at a very generic example. So if we have this reaction, A plus B gives us D plus E, and C is a catalyst. What we want is a rate law where the rate is found in terms of the concentration of A raised to some power. We want to find out what power it's raised to, times the concentration of B raised to what power. We need to find that out, times the concentration of C and what its power. And sometimes the power can be 0, and if the power is 0, remember that number becomes 1 and the whole term drops out. So this is our most generic form of the rate law. Notice that products are not involved in the rate law, just the reactants and sometimes catalysts. And also the brackets mean concentrations, and usually molar concentrations. And these exponents, M, N, and P, are found experimentally. They are often integers. They don't have to be integers. I will say that for this class, for E's in this class, we're really going to be looking at only integers, but they don't have to be. And like I said, they have to be determined experimentally. You cannot just look at you can't look at this and assume that these exponents are the same as the coefficient. So, notice that this is not little a, this is m. So m is different from a. So it might be a, or it might be something different. So these coefficients are different. The coefficients are different from the exponents. All right, so let's get a few terms in. Reaction order is just equal to the exponent of the concentration of that species rate law as determined experimentally. So in other words, let's make it simpler. The overall order just equals the reaction order just equals to the exponent, and then the overall order of the whole reaction will equal the sum of all the orders of each species. So let me give you a better example. All right, so let's consider this reaction. 2NO plus 2H2 gives us N2 plus 2H2O. After doing a lot of experiments, and we'll get into how they did it in just a little while, but it was determined experimentally that this is the rate law. So what does that mean? I would say the rate of this reaction is second order with respect to NO, because the exponent here is 2, so it's second order with respect to NO. It is first order with respect to H2, because my exponent here is a 1. And then the total order for the whole reaction, you add the exponents together. So it's third order overall. 2 plus 1 is 3. So it's second order with respect to the NO, first order with respect to the H2, and third order overall. Again, if there was, like, let's say there was a catalyst, notice that the catalyst doesn't appear in here. There's nothing else in here. So if there was a catalyst, it would be considered 0 order, because anything raised to the 0 power just turns out to be 1. So there's nothing else involved in this reaction. Like I said, reaction orders frequently have whole numbers, particularly 1 and 2. They can be fractional. They can be negative. They can be fractional. We can have 0, we can have negative orders. And they're harder to understand, but in a complex reaction, you can have them. And like I just said, the concentration, if it's 0 order dependence, has no effect on the rate, because anything raised to the 0 power is 1, so it just cancels out. And then here are the orders. So M is the order with respect to A, N is the order with respect to B, and the overall order then is M plus N. So that's my generic equation. All right, so the one way that we can determine the rate law is to use initial rates of reaction. And so in other words, we're going to run the reaction multiple times, and we're going to measure the initial rate of the reaction, and we're going to change the concentration and do it again and find the initial rate of it with different concentrations. So we run the experiment multiple times, changing the concentrations. And also notice you can only change the concentration of one at a time because you want everything else to stay constant. And then you're going to measure the initial rate, and then we'll be able to find the order. So I think the easiest way is to just do an example. But before we do that, let me just kind of go over this. So notice that, so just kind of, let's just follow this line of reasoning. If we double the concentration and the rate doubles, it means it's first order. So let me show you what I mean. So let's say rate equals, we'll just talk about A. So if it's first order, that means the exponent is 1. And let's think about that. If I double A and the rate also doubles, so in other words, this increases by 2 and this increases by 2. This is true only if the exponent is 1. So if it's first order, the exponent is 1, and this is true. Now, it doesn't have to be doubled. What if I tripled the concentration? 3 raised to the first power should be 3. Then I would expect my rate to get 3 times faster. If I quadrupled the concentration, if it's first order, then the rate should quadruple. So anything that's first power, whatever you do to the concentration, should also affect the rate to the same magnitude. Let's say, what if I double the concentration and it has a quadrupling effect? So here, again, let's do it over here. Rate equals A to the second power. So if it's second order, that means the equation is raised to the second power. So let's think about that. If I double the concentration, 2 squared is 4. That means the rate will increase by a factor of 4. So I double the concentration, but the rate increases by a factor of 4. Or what if I triple the concentration? 3 squared is 9. The rate should get 9 times faster. So that's second order. And this is important because we're going to use it in just a second. And then, let's see if I can just erase this. And then finally, if you double the concentration, if it's third order, so let's write it here, rate equals concentration to the third power. Anything you do to A has to be raised to the third power. So if you double the concentration, then the rate will get 8 times faster because 2 cubed is 8. So what we're going to do is we're going to change concentration, and we're going to see how did the rate affect it, and then we'll know, is it first order, is it second order, is it third order. That's why I said we're not doing fractions, because that would be a little complicated to think through. And then finally, I mentioned this already, if you double the concentration and the rate has no effect, that's 0 order. So let's look at that. So let's say you doubled the concentration of A. 2 raised to the 0 is 1. That means the rate doesn't change. So keep those things in mind as we go through the next example. All right, so here's some data that was given to us. Various trials and combinations of concentrations of the reactants were run, and the initial rates of reaction were measured. So NH4 plus NO2 negative to give us N2 and 2H2O. And I don't know what they measured, probably that maybe the pressure of N2. But anyway, they were able to measure the rate of the reaction right at the very start of the reaction. So notice that the first trial was run with 0.0100 molar. Probably should have the units in parentheses, but brackets mean molar, so we'll just keep that in mind. So in the very first reaction, it was 0.0100 molar NH4 and 0.200 molar NO2, and the rate was measured to be 5.4 times 10 to the minus 7th. Then notice what happened. The second trial, they doubled the concentration of NH4, but they kept NO2 the same, which is important because now we don't have to worry about the effect of NO2 between these two reactants. So let's look at what happened. So we doubled this, concentration increased by 2, this stayed the same, and what's happened to the rate? Well, hopefully you can see, because the exponent is the same, that it's doubled. So we said on the previous slide, if you double the concentration and the rate doubles, that's always first order. I'm going to show you in a minute, if you can't see that right off the top of your head, a way that you can plug the numbers in and come up with this as well. Anyway, so it looks like it's first order with respect to NH4. Well, let's look between experiment 2 and 3. So again, this is staying constant throughout these 3 first. Now, you won't always get this many. You might just change it once. But anyway, notice between 2 and 3, again, this doubles. This stays the same. And again, what happened here, this is double this. Now, I suppose 21.6 would be exactly double, but, you know, our experimental showing. So by doubling the concentration, we double the rate. And remember that that's first order. Because again, rate, let's put it in terms of this, oops, NH4. Whenever we doubled the concentration, the rate doubled. So that means M has to equal 1. I think I go through all this on the next slide. Let's just take a glance. Notice that in 4, 5, and 6, these are all the same, so we don't have to worry about NH4. And NO2 negative in experiment 4 is 0.0202. And notice that here we doubled the concentration between 4 and 5, and again we see that this has doubled. I should use a different color. And if we look at this again, we double it one more time, and again this doubles. So again, this is first order with respect to NO2. Like I said, if you hopefully you can see that. A lot of times the data is that simple where you can see, well, 5.4 doubled is 10.8. So yes, everything's been doubled. If you can't see it, what I'll show you, I think on the next slide, what you can do. So let me back up just a minute. So when you're given a problem of this type, this is how I would start. I would say, okay, I'm looking for the rate law. What's the rate law? The rate is equal to the K, some constant, times the concentration of each reactant raised to some power, so M and N. We want to find out what is M, what is N. So we said, so if we're keeping, for the first 2 trials, let's trial 1 and 2, we kept NO2 constant. So let's notice something. Just go up here. So what I'm going to do is I'm going to take the and this will just make it easier. I always take the bigger one over the smaller one. So notice that the rate for experiment 2 was 10.8 times 10 to the minus 7th, and the rate for experiment 1. So what I'm doing is I'm taking the ratio of 2 to 1, and that's rate. Now my constant is going to be constant no matter what. And now I'm going to put my concentration, and I'm going to say, and raised to the M. And the concentration of NH4 was, for the second one, was 0.020, and for the first one was 0.0100. And the NO2, I'm going to cancel out as well. So I'm going to cancel out the K, and I'm going to cancel out the NO2 because that stayed constant. So that didn't change. So this is kind of my equation that will help me look for it. So, you know, if you could see on that last slide, hopefully you can, that when you double the concentration, the rate doubles. But if you can't see that, go ahead and do the larger one over the smaller one. And it should always be larger over the smaller. They should be the same ones on the top. Anyway, if you take this and divide it, what do you get? You get 2. If you take this and you divide it, you get 2. It's raised to the m power, so we know that m has to equal 1. So that's a way that you can actually write it down and work through it if you can't see it at first. Sometimes they're a little bit harder to see. So I'm going to cross that off, and I'm going to put a 1. So we know already that it's first order with respect to NH4. Now we're going to do the same thing with the NO2 data. And I'm gonna this time the rate for the, let's do trial 5. The rate was 21.6 times 10 to the minus 7th. Oops, 7th. And trial 4 was 10.8 times 10 to the minus 7th. So that's rate 2 over rate 1. And K is constant, so I'm not worried about that. And NH4 is constant, so I'm not worrying about that. So now I'm just looking at the NO2 concentration. And NO2 for trial 4 was 0.0404, and for trial 2 is 0.0202. And this is raised to the n power. So again, we have 2 equals 2 to the n, so n has to be 1 also. So sometimes they're different, sometimes they're the same. So it turns out that this reaction is first order with respect to NH4, first order with respect to NO2, and then second order overall because you add them together. So that's our rate law. You can actually take it one step further and solve for K by using one set of data. So just pick one of the trials, it doesn't matter which one, and plug the data in. So notice that the rate for trial 1 is 5.4 times 10 to the minus 7th. The concentration of NH4 is 0.01. The concentration of NO2 is 0.2. So we can solve for K. If we divide 5.4 times 10 to the minus 7th molar per second. So here's my units for that. Molar per second divided by 0.01 molar divided by 0.2 molar. Notice that one of my molars will cancel. And so my units are actually per molar per second because it's 1 molar and 1 second in the denominator. So sometimes we might also write it like this. Remember, the -1 means it's in the denominator. So that's my K value. So my overall rate law is rate equals 2.7 times 10 to the minus 4th per molar per second times NH4 plus to the first power times NO2 negative to the first power. And what's interesting is then we could actually predict the rate if we change the concentration. So if we want to run it at other concentrations, we can plug those into this equation and find out what the expected rate law, or what the expected rate should be. This is the rate law. So let's look at another example. Iodide ion is oxidized in an acidic solution to triiodide ion as long as you've got peroxide. So peroxide plus 3I negative plus 2H plus, so that's the acidic solution, will give us I3 and 2H2O. So just like before, a series of 4 experiments was run at different concentrations of H2O. This time there happens to be 3 reactants, so it just makes it more complicated, but it doesn't make it harder. And so the initial rates of I3 formation were found, and so the data is tabulated. And we can see that here on the next slide. So again, what we're trying to do is find the rate law for this reaction. So the rate, we always start out by just saying the rate is equal to some constant times each reactant raised to some power. In this case, I don't know, you could use M, N, and P, you could use X, Y, and Z. It doesn't really matter, whatever you use. But the idea is that we can't look at it and know what the rate is, what the power is, and that's what we're going to find it experimentally. So it's looking at the data, we want to find out what K is. We want to find out what the exponents M, N, and P are. So let's look at the data. And this time I've actually written it out so that you can see. So let's write this up here. So rate equals K H2O2 to the M power, I negative to the N power, and H plus to the P power. As long as we pick two experiments or trials where everything's constant but one thing, then we can determine it. So let's look at it. And just be careful because every set of data is slightly different. Notice in the first three, the H plus is constant. So, and in the first two, the I negative is constant. And all we've changed is the H2O2. So if we use experiment 1 and 2, we can find out what the exponent is for H2O2. Let's just take a perusal. We've doubled the concentration here, and what's happened here. Hopefully you can see that that's also doubled. So it should be first order. If you want to write it out, how would I do that? I thought I wrote it out, but I think I didn't, but let's do that. So I always start with rate on the left. So 2.30 times 10 to the minus 6 over 1.15 times 10 to the minus 6 equals the concentration 2 over 1. We have to raise it to the M power. And because the I negative is constant and the H plus is constant, we can ignore it. And also the K is constant. So what we're doing is just finding out what M is to make this true. Again, this is 2. This is 2. So M has to be 1. So here's kind of what I was talking about. So the rate at for the first set of data, and then the rate at the second set of data. And this is much more complicated than it needs to be. But because for the first set of data and the second set of data, these two are the same, so that's constant. These two are the same, so that's constant. Of course, the constant should be the same, so that's constant. So that's where this comes from. And I tend to put the second one over the first one. If it depends on the way that the data is given to you, but I promise you it works a whole lot better if you put the larger one on top and the smaller one on the bottom, because otherwise you'll be working with fractions. And if you want to just make it easy on yourself, they should all turn out to be whole numbers. And so you don't want to do fractions. So again, rate 2 over rate 1, concentration 2 over concentration 1, and it's raised to the M power. And when we plug that data in, the rate for the second trial over the rate for the first trial equals the concentration for the second trial divided by the concentration for the first trial raised to the M. That turns out to be 2 equals 2 to the M, so M has to be equal to 1. So now we know what M is, and we can move on and find 2 experiments where I changes. So let's look at that. So for I negative, and here's where you really want to be careful. Yes, trial 1 and 2 change the H2O2. Let's skip over trial 2 and let's look at 1 and 3. So in 1 and 3, H2O2 stays the same, and H plus also stays the same. And now we're changing I to I negative. So if we look at experiments 1 and 3, we can find out. And we see the same results, 1 and 3. Notice that we have doubled the concentration of I negative. We've doubled the rate. And so it should be first order again. So it's first order with respect to I negative as well. But we can work through it. So, if we take the rate at trial 3 divided by the rate at trial 1 equals the concentration at 3 over the concentration at 1 raised to the n power. And again, when we plug those numbers in, we get 2 equals 2 to the n. And so n has to equal 1. So finally now we know the m and we know the n. Finally, we want to pick the data where the H plus changes, but neither of the others change. So again, be really careful. Obviously, the last one, but let's make sure that, so if we use the first one and the last one, because 3 and 4 change, but notice that the I negative are not the same. So make sure and you pick where these two are the same. So if we try experiment 1 and 4, H2O2 is the same, 1 and 4, I negative is the same, and 1 and 4, the H plus changes. And just by inspection between 1 and 4, the rate doesn't change. So the concentration doubles, but the rate doesn't change. So if you remember, that's 0 order, but let's work through it. So the rate 4 over rate 1 equals concentration of 4 over concentration of 1 to the p power. Again, I'm always picking the larger one over the smaller one to make my whole numbers. They're the same, so that's 1. This is double, so that's 2 to the p. P has to be equal to 0 to make this equation true. So it's 0 order with respect to H plus. Now that doesn't mean that you don't need it. It still needs to be there. It's just that the concentration doesn't affect the rate. So now we know what the rate law is. Its rate equals K H2O2 to the first power, I negative to the first power, H plus to the 0 power. You can write it like that, or you can ignore it because that equals 1. You can rewrite it like this. Finally, you can plug in, it doesn't matter which one you use this time, you can use experiment 1. You can plug in these sets of data for rate, concentration, and solve for K. So the reaction order is first order with respect to H2O2, first order with respect to I negative, 0 order with respect to H plus, second order overall, because you add them all together, 1 plus 1 plus 0. And like I said, you can now calculate what K is by using one of the experiments, and I happen to use the first one, 1.15 times 10 to the minus 6 molar per second. Just notice that the rate is given in seconds this time. Equals K times 0.010 raised to the first power times 0.010 times raised to the first power, and then this is not in the rate law, so we didn't include it. And if you do the math, 1.15 times 10 to the minus 6 divided by 0.010 divided by 0.010 gives you 1.15 times 10 to the minus 2 per molar per second. So this is one way of writing it, or if you wanted to, 1.15 times 10 to the minus 2 per molar per second. And this is in moles per liter, but you can keep it in molar either way. So there's my rate law. Rate equals 1.15 times 10 to the minus 2 per molar per second times H2O2 to the first power times I negative to the first power. So I believe there's some extra practice problems on Canvas as well that you can try some of these out. Note that the units of K are actually going to depend on the type of reaction you have. So notice in the last one, the last two actually, the units were per molar per second, but they're going to change depending on the overall rate or the overall order of the reaction. So if rate is first order, rate equals K times A. Here's the important thing, is that rate should always be in molar per time, seconds, or if it happens to be hours, whatever the time unit. So rate should always have this unit, molar per time. And so the K has to be such that everything else cancels out. So notice that if you have first order, rate, molar per second or molar per time, equals K times molar. Well, if molar cancels out on both sides, then my K is going to be in units of per second. Or if it happens to be per time, whatever the time units have to be. If my rate is second order, then look at what happens. Again, rate should always be molar per second. This time I have molar times molar. So what happens if I solve for K for units? I have molar divided by molar, divided by molar, divided by second. One of my molars will cancel. So now I have per molar per second, or per time, whatever the time happens to be. What if I have third order? And it doesn't matter. And just by the way, second order could be like B raised to the second power without the C there. So whatever, it's still going to be, the units are going to be the same. Third order, notice what happens is you have molar per second equals K times molar squared. I guess I reverse these, but it's molar third. One of the molars will cancel. So just one of these will cancel. And so my unit will be molar to the -2 per second. So just notice that the number, so first order doesn't have molar at all. Second order has 1 molar, molar to the -1. Third order has molar to the -2. So if it was fourth order, it would be molar to the -3 and so forth. So just keep that in mind when you need to use figure out what the units of K are going to be. All right, looks like I got one more set of data to work through. So here's the reaction, and I mix these up a little bit just so you can kind of see what's happening. So like I said, you don't always have to use the second over the first, but you always want to use the largest over the smallest. So let me just do it here on this sheet. We want to know what rate is, ClO2 to the M power and OH negative to the N power. Or you could call it XY, you could, whatever you want to do. So notice that in the first two trials, OH is negative, so we can ignore it for the time being. Notice that we've cut this down by 3. We've divided this by 3. So it's not always given to you by multiplying or whatever, but it's divided by 3. And what's happening here? So this is an example that's probably a little bit harder to see what's going on. So I'm going to plug my numbers in. So rate, I'm going to take the bigger one for trial 1 divided by trial 2 is going to equal 0.06 divided by 0.02. So it's not always double. But if we do that math, what do we get? We get 0.0248 divided by 0.00276. 0.00276 is going to give us 9. So this is 9. 9 equals 3 to the M, so M has to equal 2. 3 squared is 9. And then, so we know that M is 2. It's second order with respect to ClO2. And now let's find the data. Let me just do a different color. The data for OH negative. So we want 2 and 3 because those are the same. And this has increased. Now this time it's going up as we go from 2 to 3. And then we got that. So this is increased by 3. Let me go back to my purple and say this was this is going this way is increased by 3, and going, let's do it that way, increases by 9. So that's why that's squared. Go back to my green. This is increasing by 3, and what is this doing? Again, I don't know, but let's just plug in the number. So we'll take the rate, 0.00828, divided by 0.00276, equals 0.090 divided by 0.030 raised to the n. And again, this one, I wouldn't be able to do that in my head, so I did it on my calculator. 3 equals 3 to the n, so n has to equal 1. So if I come back up here, I change that to 1, here's my rate. Rate equals k ClO2 squared OH negative to the first power, and that's my rate law. And again, I've gotten it from my data here, so hopefully you can pause this if you need to think about it. I think I go through it on the next slide too. Oh, there it is. I got rid of it. Let's so hopefully you can see that. So the rate law, where it's m and n, that's where I kind of wrote it on top of that. And then I did experiment 1 and 2, and that's where I discovered that 9 equals 3 to the m, so m is 2. And then doing experiment 2 and 3, again, we find out that 3 equals 3 to the n, so n is 1. So that means that this n changes to 1. So that's my rate law. And then finally, I can find out what k is by plugging in one set of data. It doesn't matter which one. Be really careful. If something's squared, make sure and square that amount. So 0.0248 equals k times 0.060 squared times 0.030. K equals 0.0248 divided by 0.060 squared divided by 0.030. Notice that this is molarity squared, molarity, so these will cancel, and so my unit, so it ends up being 229.6 m to the negative 2 seconds to the negative 1. And we know it's seconds because that's in the rate law. Okay, so you might want to go back and look at those again or practice some yourself, but that's how we get the rate law from experimental data. And here's the final equation. And like I said, we can use this equation then to determine other concentrations. Like, let's say, what will the initial rate be if ClO2 is equal to 0.01 and OH negative is 0.015? So those are different from what we ran earlier. We should be able to predict what the rate is. We just plug it in, 229.6 times 0.010 squared times 0.015 gives us 3.4 times 10 to the 4th meters per second, and your rate should have the meters per second unit. And our units cancel.